Olá, boa noite. Iremos iniciar o nosso primeiro webinar da SBE, com a participação do professor Ricardo Salazar, da Pontifícia Católica é, do, do Chile. O professor Ricardo é professor associado da Faculdade de Química e Farmácia da Escola de Química da Universidade da PUC do Chile. Atualmente é o diretor de extensão e educação continuada da mesma faculdade. Possui doutorado em Química na Universidade do Chile, pós-doutorado na Universidade de Santiago do Chile, assim como também na Universidade de Barcelona. Trabalha nas linhas de pesquisa em eletroquímica, química ambiental, processos avançados de oxidação eletroquímico, eletroquímica orgânica e descontaminação da água. Possui principais projetos de pesquisas financiados, inclusive alguns com colaboração com pesquisadores brasileiros. Atualmente supervisor de 6 pesquisadores de pós-doutorado, 14 graduações e 17 alunos de mestrado e doutorado. Possui mais de 100 artigos, com fator H, índice H32. Possui 3 capítulos de livros e diversos outros trabalhos publicados em anais de eventos. O professor Ricardo vai iniciar o nosso webinar quando quiseres, professor.
Obrigado, Guilherme, pela apresentação. Hello, everyone. Thank you very much for the invitation today. And greetings to all my Brazilian friends. For today, I have prepared a conference that brings together some of the most important results of our research group on the use of electrodes for water treatment. ¿Me escuchan bien, William? ¿Todo bien? It is okay, William?
Sim, tudo ok.
Okay.
Escutamos bem.
Perfect. Well, there are different initiatives worldwide focused on water conservation, which focus on water reuse as well as reducing pollution. Among them, we can highlight the One Health project from the World Health Organization, or the Sustainable Development Goals, and the Nexus project. As I mentioned before, their main objective is protect water from different angles. The world actually more than 80% of wastewater is discharged into surface water without any kind of treatment. And this problem produces the contamination of water, but the problem increased because with this contaminated water, this water is used for irrigation. Even in countries as Brazil or Chile or Colombia, the use of water with a different level of contamination occur today. And on the other hand, the problem related with the scarcity of water continue to increase with the years due to the global warming. And the problem with the contamination of water in the last years is focused to the presence of organic pollutant in low concentration called contaminant of emerging concerns or micropollutant. In Latin America, Brazil, Chile, Colombia are the main countries that have conducted research on the presence of these micropollutants in biological and aquatic compartments. Data from these countries gathered indicate that pharmaceutical, pesticides, and personal care products are the most assessed contaminant of emerging concern, being the most common, for example, in Brazil, pharmaceutical compounds as antibiotic or diclofenac, paracetamol, and the scenario is similar on the rest of the countries of the continent. And the detection of this kind of compounds were observed near to the urban areas, which confirmed that the out-of-date wastewater treatment plants and sanitization infrastructure limiting the removal of this kind of pollutant. The contaminant of emerging concerns are chemical or microorganisms not commonly monitored in the environment, but that have the potential to enter to the ecosystem and cause adverse effect on human health and the environment. These contaminants include, as mentioned, personal care product, pesticides, pharmaceutical, and actually we have a list, a global list of emerging contaminants, including more than 10,000 different chemical compounds. As in the industrialization and urbanization progress, these contaminants enter the environment through domestic, industrial, agricultural activities. And the main concern is that many of these contaminants are not completely removed by wastewater treatment plants, allowing them to reach water bodies, surface water, underwater, or seawater. The effect of emerging contaminant can be subtle yet significant, impacting aquatic life and ultimate the human health. For example, some of the substances act as endocrine disruptors, altering hormonal functions in different organisms. And additional, the antibiotic resistance can increase due to the presence of antibiotics in water body. Today, we have this system to treat wastewater. For example, we have wastewater treatment plant. Common wastewater treatment plant produce treated water or treated wastewater. Some of them produce energy and biosolids, but this biosolid contains some pollutants too. And the idea is that in the future we have to look for a waste resource recovery facility with a biofactory that produce reclaimed water with reuse of water, a safe reuse of water, energy with biogas mainly, biosolids without contamination, and the recovery of nutrients and materials, for example, nitrogen, phosphorus, or other ions of interest. So the idea is that wastewater should be considered as a resource to be used. The problem is that wastewater contain this kind of pollutant, and they are recalcitrant, and it's not easy to the elimination from wastewater. So we need increase the efficiency of the treatment, decrease the requirement of energy, thinking a total process, a sustainable total process with a low operation cost. With these challenges, we can reduce the exposure to the pollutants, and we don't have the problem with the exposition to this kind of pollutant for human health. In this sense, with our research group, we study the electrochemical processes or electrochemical technologies to treat wastewater containing different kinds of organic pollutant. We apply different electrochemical advanced oxidation process as electroxidation or anodic oxidation, electrophantom and photoelectrophantom processes, and the photoelectrocatalysis. These processes produce strong oxidant as a hydroxyl radical, and this hydroxyl radical reacts with the organic pollutant until its complete elimination or its complete mineralization to carbon dioxide. On the other side, the electrocoagulation is another electrochemical technology different to the electrochemical advanced oxidation processes. And now we will I will describe the different processes and the characteristics of the electrodes used for the water treatment. In the case of electrochemical advanced oxidation processes, we have an electrochemical cell containing an anode and a cathode immersed in the contaminated wastewater, or the wastewater containing a different kind of pollutant. So in the anodic oxidation occurs the oxidation of water. The same contaminated water is oxidized on the anode surface, producing hydroxyl radical physisorphed on the surface of electrode of the anode. These hydroxyl radicals react with the organic compounds, producing oxidized intermediates. Even the complete transformation to the organic compound to carbon dioxide. The efficiency and all these characteristics that I mentioned before, the cost, the sustainability, the versatility of the anodic oxidation depend mainly on the characteristic of the anode surface. In the case of electrophantom process, the main reaction occurs on the cathode. We produce hydrogen peroxide on the cathode surface by the reduction with 2 electrons of oxygen. This hydrogen peroxide react with the small concentration of iron 2, producing homogeneous hydroxyl radicals that react with the organic compound to complete mineralization to carbon dioxide. This is the classical Fenton reaction, and the iron 3 produced from the Fenton reaction is reduced on the same cathode surface, being the process more catalytic. If the system is irradiated with the UV light or sunlight or UV radiation from the sun, we obtain an increase of the efficiency due to the photocatalytic activity of iron 3 compounds. For example, we can observe or produce the photoreduction of iron 3 complexes, producing the Fenton catalyst and the hydroxyl radical. increasing the mineralization or degradation of the pollutants in wastewater. And during the degradation of the pollutant, we can produce intermediates like carboxylic acid. And this carboxylic acid forms a complex with iron 3, and this complex can be photolyzed, photoreduced with the UV radiation, producing the carboxylation and increasing the concentration of iron 2, producing more of the Fenton reaction, and consequently, more concentration of hydroxyl radicals. This is the typical electrochemical cell used in electrochemical advanced oxidation processes. So remember this schematic electrochemical cell because permit to explain all the processes with the different electrodes for the anodic oxidation or electrophenton processes. In the literature, we can find different studies about the electrophenton process, anodic oxidation process, or variation of these electrochemical processes for wastewater treatment, with mainly focused in the modification of anodes or cathodes, even, for example, with microorganisms, like a bioelectrophenton process, or assisted electrophenton process. For example, with sun radiation, that is the photoelectrophenton process, or with ultrasound, this the sonoelectrophenton process. So when we have the electrochemical system, we can study the characteristics, the advantage, or the increase of the efficiency of the process based on the performance of the electrode, study with different instrumental technique or analytical techniques applied for this kind of studies. For example, with the spectroscopy techniques or analytical techniques based on spectroscopy, we can study directly the surface of the electrode, the zone of the double layer on the electrode, or even the solution. With the microscopy techniques, we can study the surface of the electrodes and the double layer area. By chromatography, we can study the change in the solution, and with the change during the electrolysis, we can relate the change in the solution by chromatography techniques with respect to the performance of the electrode. And with electrochemical techniques, we can study the surface and the bulk of the solution too. So we applied these techniques, the analytical techniques, to study or related the behavior of the electrode with respect to the treatment of wastewater. Several years ago, Comninelli proposed a classical mechanism to describe the performance of the electrodes during the wastewater treatment, specifically for the anodes in anodic oxidation or electrochemical oxidation. The surface of the anodes, where occur the oxidation of water, produce hydroxyl radicals. These hydroxyl radicals can be physisorb on the surface, and these physisorb radicals react with the pollutants in the solution, producing the complete mineralization to carbon dioxide and release the surface again. If the interaction of the hydroxyl radicals are strong with the surface, an oxide on the surface is produced, and this oxide can react with the pollutant, producing a partial oxidation of the pollutant and releasing the surface of the metal. If the mechanism is from the complete mineralization of the pollutant due to the easy reaction between hydroxyl radicals with the pollutant, this kind of electrode is called a non-active anode. Instead, that kind of anode where the interaction of the hydroxyl radical is strong with the surface, we have active anodes. So we have different kind of electrodes in this kind of family of electrodes. But the scenario is different when we have, for example, a synthetic wastewater with one pollutant with respect to the composition of a real wastewater. In a real wastewater, we have different kind of ions in the solution, cations, anions, or different salts. So we have the oxidation of water on the surface of the electrode, producing hydroxyl radical. But if the water contains chlorine, we have the oxidation of chlorine to chloride, producing hypochlorite by reactions on the anode surface, in the diffusion layer, and in the bulk of the solution. We can produce persulfate, different chlorine reactive species, peroxide, or another radical species. All this depends on the composition of the wastewater. So boron-doped diamond electrodes are the most common electrode for the wastewater treatment. They have the possibility or the capacity to produce high concentration of hydroxyl radicals. By ECR spectroscopy, we can obtain a response of the generation of hydroxyl radicals on the anode surface, trapping with the DMPO trap, producing the adduct with a hydroxyl radical, and the composition of the BDD electrodes is crucial for the production of higher concentration of hydroxyl radicals with respect to another. If you know, diamond is a poor electricity conductor. So in the crystallographic surface, we need different boron atoms doped the surface of the BDD electrode, increasing the conductivity for the production of the hydroxyl radicals. So we have, for example, two kind of BDD electrodes. One of them with a high concentration of diamond with respect to another BDD electrode with higher concentration of graphite. We have the ratio between graphite and diamond on the electrode surface. When we have a higher ratio of diamond on the BDD electrode, a higher concentration of hydroxyl radical is produced. So BDD electrodes is a bad catalyst for the oxygen reaction, for the oxidation of oxygen, sorry. And for this reason, for example, another kind of electrodes, as for example, electrodes containing metal oxides, produce more of other oxidants than hydroxyl radicals. For example, in the case of BDD electrodes, here, the presence of hydroxyl radicals on the surface of BDD produce the interaction of this with chlorine, producing chlorine oxide species. And in a higher concentration, for example, instead that this kind of electrode produce more concentration of chlorine and then hypochlorite in the solution. But at the same time, when the production of hydroxyl radicals, we can produce persulfide, peroxide, or if we modify the surface of the electrode, we can produce more concentration, for example, of hypochlorite than chlorate ion in the solution. The presence of a diamond on the surface of the electrode produce, as mentioned before, a higher concentration of hydroxyl radicals. If you have an electrode with high concentration of diamond, we can reach fast degradation. For example, in a real wastewater, we can remove or degrade a higher concentration of the organic contents of the wastewater from a winery industry. And we can determine the concentration of the presence of the hydroxyl radical by ECR experiments. With respect to the surface of the electrode, for example, we have different kinds of BDD electrodes with, for example, different proportion of graphite and diamond on the surface with different substrate, silicon and niobium, and with different concentration of boron on the surface. In the case of BDD, with different concentration of different ratio of diamond, these have more diamond than this electrode, present a high roughness on their surface, which is of the polycrystalline type. And this roughness depends on the diamond and graphite ratio. If we increase the magnification here, you can see it is possible to observe a great number of defects on the surface, and these defects are higher when we have more concentration of graphite on the surface. When we change the support from, for example, this is the same ratio of graphite and diamond, but with the same concentration of boron, but with different support. This is silicon and this is niobium. The surface and the morphology will not affect it with the support. But if we increase here, we increase the boron doping, change in the morphology are observed because the boron introduced into the polycrystalline phase, causing a more amorphous surface. And this morphology is known as rod-like morphology. And when we increase the content of diamond on the surface, we obtain a higher overpotential for the oxygen evolution. This is related with the higher concentration of hydroxyl radical, and for this reason, we obtained higher degradation of the pollutant when the diamond is in higher concentration of the surface. If we study with electrochemical techniques, we can observe an homogeneous active surface on all electrodes We have here two kinds of electrodes. This is with the scanning microscopy, electrochemical microscopy, and you can see that the surface is homogeneous in all of the surface of the electrodes. And by the use of the Nyquist diagram and rounded circuits, we can see that, for example, with different BDD electrodes, we can modify the resistance and the constant for the charge transference. For example, the electrodes with niobium has a lower resistance with respect to the silicon electrode, with the silicon support for the BDD electrodes. And depending on the electrode, we can obtain different mechanisms from the reaction, because the concentration of the kind of the oxidant produced on the surface electrode produce different organic byproducts. If we have chloride on the solution, we obtain organochlorines byproducts, but as the electrolysis continues producing oxidants, these hydroxyl radicals react with these organic byproducts, producing short-chain carboxylic acids, mainly oxamic acid, oxalic acid, formic acid, and this acid reacts with the hydroxyl radicals, producing the complete transformation of the pollutants to carboxyl dioxide. If we have, for example, in this work, we have a mixture of 30 compounds with different chemical characteristics, and all of them were completely mineralized to carbon dioxide. On the other hand, for example, in a work where we studied the mineralization and degradation of aniline, aniline is an industrial compound. At the beginning of the electrolysis, we observed the formation of oligomers from the oxidation of aniline on the anode surface and the interaction with the hydroxyl radicals. But as the electrolysis continues producing hydroxyl radicals constantly during the process, these oligomers were destroyed, producing aromatic compounds and then carboxylic acid up until the complete transformation to carbon dioxide. Well, the mainly conclusion of the BDD electrodes is that we can modify the efficiency in the production of carbon hydroxyl radicals if we modify the electrode surface, increasing, for example, the quantity of diamond on the surface and the doping of boron. And if we change the support of the boron doped diamond electrodes, we can't change the surface, but we can decrease, for example, the resistance to the charge transference. On the other hand, in the case of active electrodes, we have the high efficiency of mixed metal oxide electrodes to treat with water. This kind of electrode use, for example, ruthenium oxide, iridium oxide, and tantalum oxide. This kind of oxide are very good catalysts for the chloride oxidation reaction and the oxidation of oxygen on the surface of the electrodes. The presence of ruthenium oxide and tantalum oxide produce a surface, an heterogeneous surface with a cracked surface. You can see this very common structure on this kind of electrodes. The presence of the ruthenium oxide and tantalum oxide produce a very high surface electroactive area. And a difference of the BDD electrodes, the surface, the electrochemical active surface is very heterogeneous. You can see here that we can see peaks of the current on the surface of the electrodes. But when we have a mixture between ruthenium and iridium oxide, this cracked surface is homogeneous on the all electrode, and you can see that in this case the surface, the electrochemical active surface, is very homogeneous in all of the electrodes. And here you can see the presence of different oxides from thallium, iridium, and ruthenium. This kind of electrodes produce a high concentration of chloride on the solution, and the presence of chloride produce hypochlorite, and they have a lower overpotential to the evolution of oxygen and chlorine, a difference with respect to BDD electrodes, where the overpotential are higher when you use a BDD electrodes. And you can see the presence of different oxides with respect to this kind of electrodes with this composition. And we used this kind of electrodes to treat with water containing antibiotic. And you can see a very fast elimination of the pollutant in the presence of chloride in the solution. And this kind of system, you can irradiate it, increasing the degradation of the pollutants in the solution. So you can see different electrodes with different characteristics for the use in oxidation processes. If we go to another side of the electrochemical cell, we have the cathode. And for the cathode, we try to improve the performance for the cathode in the production of hydrogen peroxide for the electrophoton process. So commonly, you can find in the literature that the best electrode for the production of hydrogen peroxide is the carbonaceous cathode, because the carbonaceous cathode contain catalytic sites where the reduction of oxygen is better than in another material, because the carbon material contain imperfections or groups, oxidized group that attracted to the oxygen and improve the oxidation or reduction, of the oxygen on the surface. And this oxidation occurs by two electrodes to produce hydrogen peroxide. So we have modified different kind of electrodes with different kind of carbon materials. In this case, we used carbon black, graphite, and activated carbon to produce a more stable and resistant electrode, because a common carbon electrode are very fragile. So if we want a big electrode for a real wastewater treatment, we need an electrode that resists a lot of hours producing hydrogen peroxide with a long period of times. So we use, for example, the modification of a metallic foam. In this case, is a aluminum foam, and we painted the aluminum with a suspension of different carbon materials. We used the carbon graphite, black, and activated carbon. We produce ink, a suspension with the carbon material. We painted the electrode, and we observed the performance during the time in the production of hydrogen peroxide and the resistance with a long period of electrolysis. And here you can see the same images of, for example, in this case, we have the aluminum electrode, the aluminum covered with the materials, and here you can see, for example, in the case of carbon black, the complete modification of the aluminum surface with the carbon material. And for example, here we have the Raman spectra. This is the material. This is activated carbon with the classical D and G signal of the carbon structure. Here is the graphite. Here is the carbon black, and this is the ink prepared with this material, and we have the study of the surface of the outer of the foam, and we can see in the inside of the foam. This is the inner plane, and you can see the modification out and inner of the foam, of the aluminum foam. The best performance was obtained with the carbon black, because you can see physically, we can see the complete modification of the aluminum with the carbon black. You can see here that the metal is completely covered with the carbon, and we obtained the higher concentration of electrochemical generation of hydrogen peroxide using this electrode. So with this electrode, we apply the electrophantom process in this system. We have the reservoir with the real secondary effluent from a wastewater treatment plant. The injection of air, because from the air we obtain the oxygen to produce the hydrogen peroxide. Here is the electrochemical cell where all this reaction that I showed before occurs, and the system is recirculating during a different period of time. So we study the increase during the electrolysis time of the hydrogen peroxide and the elimination of the contaminant of emerging concern in a real wastewater. So this is the concentration of different pollutants present in the wastewater. And when we apply after 30 minutes of electrolysis, we reach almost the complete elimination of almost all pollutants present in the real wastewater. This was without the addition of supporting electrolyte. We used the real wastewater without any change applying our system for the production of hydrogen peroxide. And the electrode was used multiple times, and you can see that the same electrodes produced almost the total elimination of the pollutant. And we produced different aluminum electrodes modified with carbon black with different size of porous, and the performance was very similar. In other work, we applied the solar photoelectrophoton to the removal. Okay, sorry. No. I have a video, sorry. The technology. Here. We use an open photoreactor to produce the direct interaction between the solution with the sun radiation. So we produce hydrogen peroxide in an electrochemical filter press cell containing a carbonaceous cathode with graphite and an anode containing ruthenium and iridium oxide. And we produce hydrogen peroxide, and with the Fenton reaction, the hydroxyl radicals in the solution and on the surface of the anode. And then the interaction of the solution with the sun radiation to produce the photodecarboxylation and the photoreduction of the complexes of iron 3. And you can see the complete decolorization of the solution. This experiment is an electrophoton process because it's inside of the laboratory. When we study the hydrogen peroxide production, you can see that the concentration of peroxide increased with the applied current density. If we have a high density current applied, we observe a higher concentration of peroxide with very good efficiency. In this kind of processes, if we have more than 30% or 40% of efficiency in the production of hydrogen peroxide, it's a good efficiency. And in the solar photoreactor, this is a photoreactor for 30 liters. We work with 15 liters of the solution. We observed in different sample points that the distribution of peroxide is very homogeneous in all of the photoreactor, because you can see that the production and the distribution of peroxide is homogeneous in different sample points. So with this result, we applied the photoelectrophoton process and study that the pollutant, the concentration of the pollutants is maintained during 3 hours of the solar photolysis. If we have only the anodic oxidation, the decolorization of the solution is a little more than 50%. And we obtained the complete decolorization when the electrophoton and solar photoelectrophoton process were applied. But when we analyzed the total organic carbon of the solution, the total organic carbon is related with the complete or the mineralization to the organic pollutant to carbon dioxide. Only with solar photoelectrophoton process, only applied solar photoelectrophoton process, we obtain the complete mineralization of the pollutant in the solution. So we obtain not only, if we want For example, for an industrial process, or if the industry require only the decolorization of the solution, you can apply the electrophantom and solar photoelectrophantom process. But if you want to obtain a better quality of the treated wastewater, you have to apply the solar photoelectrophantom process, because you obtain the complete elimination of the pollutant. When we use the system in a real treatment of a real wastewater, we have a problem with the electrophantom process. The problem, or the main problem, is that we have need iron in solution. The pH of a real wastewater, for example, from a municipal wastewater treatment plant, the pH of this kind of water is between 5 and 8. At this pH, the iron precipitate, so we can't produce the phantom reaction. So in this work, we treat the real wastewater using a complex between iron 3 and EDDS. EDDS produce a complex with iron 3, maintaining iron in solution, and this complex is photolyzed with the UV radiation from the sun, producing iron 2. Iron 2 goes to the phantom reaction, react with the peroxides, producing hydroxyl radicals. So we can work or treat this real wastewater in our solar electrochemical Raspberry Pi reactor without change in the pH of the solution, of the real solution. So we study the elimination of contaminant of emerging concern in very real experimental condition. So for this study, we prepare a chemometric analysis. So we study all of the variables we looked for the best experimental conditions. So we determine the best current density during the process, the concentration of the I complex, and the time when we have to add the complex to the solution. And we have a mixture of contaminant of emerging concern of 800 micrograms per liter. So the treatment of a secondary effluent containing this contaminant of emerging concern showed the complete or more than 80% of degradation of the pollutant before 30 minutes. This is each pollutant. Here is the mixture of pollutants. And the decay of the concentration of the pollutant occurs at the same time of the decay of the concentration of the complex during the process. This is because here occurs the photolysis of the complex. The complex produces iron 2. Iron 2 reacts with the hydrogen peroxide here and producing hydroxyl radicals, and hydroxyl radicals react with the pollutant, producing the complete elimination of that. And after the 30 minutes, when we don't have a complex, increase the concentration of peroxide. During this period of time, the peroxide is produced, but the peroxide react with the complex, producing hydroxyl radicals for the reaction with the pollutants. And at the same times of the decontamination of the solution, we study the disinfection of the wastewater. So We followed the inactivation of different microorganisms. We studied the inactivation of E. coli, total coliforms, and Enterococcus fecalis, and we observed the complete inactivation of these microorganisms during the same experiment of the contamination with the contaminant of emerging concern. Well, we have anodic oxidation, electrophoton process with different characteristics of the electrodes in the efficiency to produce oxidants. And in the last time, we have worked with the group of Professor Maria Valnice Boldrin from Brazil, and with the different students from her groups comes to Chile to prove their electrodes in the wastewater treatment. We applied the photoelectrocatalysis. The group of Professor Boldrin Zanoni produced these electrodes, these semiconductors, in a semiconductor photocatalyst. We have an electrode jump to the from the valence band to the conduction band because a photon interacts with this material, producing holes and electrodes that produce finally reactive species to react with the pollutants. And the work with the Professor Boldrin, Maria Valnice Boldrin, consists in the modification or the generation of catalysts based on metal organic frameworks, different kind of MOFs, and we treat real wastewater from a secondary effluent from a wastewater treatment plant. So we study the elimination or the degradation of organic pollutants to produce carbon dioxide or final byproducts using different surface of the photocatalyst. In this work, we used 3 different photocatalysts based on MOF structures. Here, the kind of the photocatalyst, they have the nanotubes structure, and we demonstrate that with the different photoanodes, we produced hydroxyl radicals and we produce superoxide anion. Both the hydroxyl radical and superoxide react with the contaminant of emerging concern. We studied the elimination of diclofenac, sulfamethoxine, and carbamazepine. And only by photoelectrocatalysis, we obtain the complete elimination of the mixture of the pollutant in the real wastewater. And in another work with the collaboration with Professor Valnice, we used a filter. We studied the filtration, and this filter contained a photocatalyst, and we studied the elimination of sertraline. And sertraline is concentrated in the filter, and then the filter is irradiated. And we study, for example, the complete elimination of sertraline with different fluxes. We study that only with the combination of photocatalysis and filtration, we obtain the complete elimination of the sertraline, and we demonstrate the generation of different oxidants in the using this photocatalyst. That was the photocatalyst used during the degradation and elimination of sertraline. So we have that here. We have the combination of 2 processes: the filtration where the pollutant is concentrated on the surface of a filter, and then the filter was irradiated, producing oxidant species that react with the pollutant until this complete elimination or degradation. And we use continuously this material. So we reviewed the electrochemical advances oxidation processes, and finally, I would like to talk about the electrocoagulation. Electrocoagulation belongs to the electrochemical technology, but isn't an electrochemical advances oxidation process. The electrocoagulation consists in the oxidation of an anode, producing an electrocoagulant. This electrocoagulant contain high enthalpies of attraction for the pollutants, and for example, the most used are aluminum and iron as anodes. So, for example, in the case of iron is oxidized on the surface, producing this kind of compounds. These compounds are solids with and they have different charge, electric charge, to attract the compounds. And on the cathode, we can produce hydrogen gas. So we have settling flux and suspended flux. So here in the electrocoagulation process, not occur the degradation of the pollutants. Here occurs the removal of the pollutants from the solution, because we move the pollutant from the solution to another phase, and a solid phase with the electrocoagulant or flocculant. And during the anodic oxidation, we can produce different species of aluminum or iron, depending on the electrode that you use to the experiment. For example, in the case of iron, we can produce hematite or different iron oxides. This kind of oxide from iron or from aluminum can remove a very high variety of pollutant from wastewater. The electrocoagulation process occurs a very short electrolysis time. For example, we apply the electrocoagulation process with iron and aluminum electrodes in a pilot system. We treat industrial swine slaughterhouse with water. This is a very complex wastewater, and you can see that this is the quality of water after the electrocoagulation process. And here you can see the TOC decay of the water. The total organic carbon remain in the water close to 20%. We can remove from the solution almost the 80% of wastewater. And the electrocoagulation process can be applied without the addition of supporting electrolyte. So you can use the conductivity or the salinity of the real wastewater without the addition of the supporting electrolyte. But if we want to increase or decrease the electrolysis time or increase the efficiency, we can add salt to the solution. The electrocoagulation process, in the electrocoagulation process, we can use different kind of iron or aluminum electrodes from, for example, from the materials to recyclage. So we can use different kind of iron or aluminum materials to treat wastewater by this technology. And we can obtain not only the decolorization of the solution or the removal of organic and inorganic pollutants in wastewater, almost the disinfection of the water and the easy removal of the flux from water. So finally, my reflection is that there don't exist at this moment the best electrode for a global wastewater treatment. The process, electrochemical advances oxidation processes or electrocoagulation must be analyzed with respect to the kind of water, the quality of the water, the quality of the initial wastewater, and the quality of the water that I want to produce. So if you, for example, in Chile, we have very good, very strong sun radiation during a lot of period of time during the year. So in this case, in the case of Chile, the solar photoelectrophoton process is a very good option for the wastewater treatment plant. In another case, if you have an industrial specific wastewater, you can apply, for example, the electrocoagulation in combination with another process or the photoelectrocatalysis of the wastewater with a low concentration of pollutants, for example, in a pharmaceutical industry with low concentration of antibiotic, is a very good option to treat wastewater with a low concentration of pollutants. So you can apply different electrochemical processes to treat wastewater, to destroy contaminant or remove contaminant, always analyzing the characteristic of the water and the water, the initial water and the final water. And with this information, you can decide which kind of electrode you can use to treat the water, the wastewater. So I would like to thank to my university, la Pontificia Universidad Católica de Chile, to my research projects, to my groups. Here is my group, and thank you all of you for your very kind attention. ¿Cuánto me demoré?
Thank you, Ricardo. Perguntas, o público pode fazer perguntas, escrever no chat, e a gente vai selecionar.
Posso mover da apresentação? Ou... Sim?
Sim.
Ok. Ok.
Estamos aguardando.
No tengo preguntas aquí. ¿O comments? Sí. No.
Pessoal, alguma pergunta ao professor Ricardo?
Posso tentar responder en portuñol para que...
Pode ser em portunhol. Ok, eu tenho uma pergunta.
Bueno,
Ricardo, what's the more challenges in the advanced process from electrochemical systems, like for the wastewater? We know it's not much easy to make the treatment, but I think we have a lot of challenges in this area. What do you think about?
I think that we have to think the process not only as a one process. We have to combine the electrochemical process with another process, physical process or biological process. I think that the challenge is the relation between different technologies to produce water with a best quality. And on the other hand, is to think always thinking the real application. When we, yes, for example, we can obtain very beautiful SEM with a very incredible modification of the electrodes. But when you use the electrode with a real wastewater, with a real content of salt, with a chloride or solids or microorganism, this beautiful electrode must be efficient in the production of hydroxyl radicals or another oxidant. So always, I think that it's necessary to think the problem or the proposal considering the final application and the real situation.
Ok. Eu acho que vai chegar uma pergunta, Ricardo. You have another one. Acredito que o Henrique Lima Lopes.
Hola, Enrique.
Rafael, a gente tem alguma pergunta?
Okay, comments. Me mandan saludos.
Because the presentation was so clear.
Or not.
Or not.
No. Bueno.
So, I think we don't
If
have.
you have any doubt, you can write me to my email,
Okay.
or I have my social media in LinkedIn, for example, or Instagram. You can write me if you have any doubt or any comment, and I am happy to answer you.
Okay. Thank you, Ricardo. So, on behalf of the Brazilian Society of Electrochemistry and Electroanalytical, eu say thank you, muitas gracias, obrigado pela sua apresentação. Acredito que o público tenha gostado, tenha ficado uma apresentação bem clara na área de tratamentos avançados de forma eletroquímica, em nosso primeiro webinar. Você estreou o nosso primeiro webinar da SBE. Muito obrigado. Muito obrigado a todos que estiveram participando do nosso webinar. A nossa lista de frequência ficará disponível em até 5 minutos após a finalização da sessão. E qualquer dúvida aí, vocês podem com certeza escrever ao Ricardo. Ricardo, muito
Sí.
obrigado pela sua apresentação. Obrigado. Muitas gracias.
Thank you, William, for the invitation. Obrigado por la invitación. Muchos saludos a todos los amigos brasileros. Muchas gracias y espero verlos pronto. Muchas gracias por pensar en mí para el primer webinar.
Imagina, obrigado.
Bye. Chao, gente.